Hi, now that we have derived the Langevin equations for quantum mechanics, we may now make simulations of the Langevin equations to see a number of interpretation issues that we have advanced, and now we can, of course, make these simulations to see how they can happen in quantum mechanical systems. The first item that we want to show is the distinction between behavior and nature. What we want to show is that a corpuscular nature can behave in a way of a wave, and this eliminates the notion of duality, the need of assuming some sort of duality, because we separate our elements of interpretation into two different levels: level of nature, which is an ontological level, and the level of behavior, which is, as I called, an epistemological level. So we may now represent the reference of the function psi, the probability amplitude, as referring to the wave behavior. The psi itself represents the wave behavior, while the position variable represents the corpuscular nature, the position and other elements of the equation, for instance, the electric charge and mass, and maybe other elements that appear in the Schrödinger equation. So we may say that this is valid both for both for ensemble and single systems. Of course, when we may make the simulation both for ensemble and single systems, and this is what we want to show in the simulations that we will now present. Now we have here a program that I have made myself, which implements the Langevin equation for a number of systems. Here we have two systems, the harmonic oscillator and the Morse oscillator. We will be talking about the harmonic oscillator. Sometimes I will show you also the Morse oscillator. And here we are assuming that we are using the single system approach, because we are making the simulations for just one trajectory. And we will observe this trajectory, this particle, of course, for 400,000 points in the trajectory. This, of course, represents a time window. Here are the other element of the simulation, which is the gamma factor. I have already put here the gamma factor that gives the correct answer for the system. You will see in this window the appearance of the probability density function in X. Here is the function that we expect, the theoretical function for quantum state in n equal to 0, the ground state. And you will see that we have first the appearance of a wave. We must have here behavior that is quite different from the usual expected behavior, because we have transient states, and while the system does not converge to the quantum mechanical one. And at the end we will see that we have exactly the quantum mechanical state that is presented here as the continuous line. So let's make the simulation. I will start that, and we will compare the fulfillment of the configuration space here in terms of time. Let's go. Look what begins to happen. The particle is filling the configuration space, the projection of the phase space, and it's filling in such a way that it gives in the end wave-like behavior, since this density function is just the solution of the Schrödinger equation, of course the solution in terms of density. So look that when we compare the result of the simulation of a single system with the result of the Schrödinger equation, the two uh, results match perfectly. We may have even better results if we uh, increase the number of points in the trajectory. Of course, this will give us a better result because we will include more numbers in our approach. We may also make the same calculations for an excited state of the harmonic oscillator. Let's do that. I will now simulate the same system. Note that the gamma factor changed, but the number of trajectories is the same because we are also assuming here a single system simulation. So again, we have the density in the configuration space like this. This one, this result is of course the previous result. It will disappear when we begin to make our simulations. So let's make the simulation again. Now look what is going to happen. We have exactly the same sort of behavior that was shown for the ground state. The system uh, begin to the particle begins to fulfill the configuration space cells, and when it does that, it makes it appear the result of the probability density function in configuration space, which is related to the first excited state. We can do the same thing for the second excited state. In this sense, now we have this probability density function. We can now simulate it again. Note that the particle is fluctuating and filling the configuration space cells. It will take some time for doing that. Note that in this case, the time that it takes to get the asymptotic solution is larger because it has to transit between these two regions here, the left, right, and the middle region. And for a single system, we will sure have to have a little more points to represent the relation. This result is better if we make the ensemble simulation, but we will leave this discussion of single systems and ensemble for a different time. So this is what I will have to show in this moment. Let's go back to our presentation. In the next video, I will show how fluctuations appear in quantum mechanical systems by showing the behavior of a Morse oscillator. Thanks for watching.